In this video, I'll go over drawing organic structures. To represent organic structures, there are three ways. Structural formula, which is the regular Lewis structure that you already draw. And here we're showing all carbons, hydrogens, and all the bonds, whether it's a sigma or a pi. This structural formula has another name, either a bond line or Cookly, and I've used both terms in the problem sets on eCampus. Another way to represent an organic structure is using condensed formulas. And in these, you only show carbons, hydrogens, you don't show any bonds. And the skeletal form is the line bond form, where you show just bonds and you don't show carbons and hydrogens. Most of our organic structures will be represented by a skeletal form because it is the easiest. Let's have an example. Given a molecular formula of C5H12, C5H12 is a hydrocarbon because it's made up of carbons and hydrogens. And we said at the beginning that hydrocarbons are classified into alkanes, alkenes, and alkynes. So each one has its own molecular formula. Alkanes have a formula of CnH2n plus 2, and that structure here fits the CnH2n plus 2, so I know exactly it is an alkane. We'll talk about the molecular formulas of alkenes and alkynes as we proceed. So I know now that it's all single bonds in there. Now, you don't have to calculate the valence electrons because this is a simple structure, but remember that structural formulas, these are Lewis structures after all. So, but this one is a simple one. So the first thing that you would need to do is connect all the carbons together. So draw the backbone, forget about the hydrogens, okay? Connect all the carbons together. So I have 5 carbons, so go ahead and connect them together. And then after you do this, we know that every carbon should have 4 bonds. So go ahead and place the bonds around each carbon, the convenient bonds in there. So I know that this carbon will have 3 bonds around it. This carbon will have 2 remaining bonds around it. And this one is going to be 2, this one is going to be 2, and this one is going to be 2 in order, or 3 actually, to complete the 4 bonds for every single carbon. And then fill your hydrogens. So again, you draw your backbone of your structure. So here you go, draw the backbone of your structure and make sure that every carbon has 4 bonds in there. This is how you do it. And then after you fill the bonds, go ahead and fill those bonds with hydrogens. This is called the structural formula, and it's a detailed one, as you can see. And as the molecule gets bigger, the structure gets bigger and more complicated. So this is the structural formula. Now for the condensed. For the condensed formula, you start always reading your structure from left as you write. So from left to right, never ever read it from the right, read it from the left. So as you read, you go. And then structural formulas, you don't show any bonds. So see those CH bonds in there, we're going to get rid of those. The CC bond, we're going to get rid of those as well. So for the condensed structure here, we're going to start with the first carbon. This carbon is going to be a CH3. See it? So this carbon has 3 hydrogens around it. So we're going to term it as a CH3 in there. So you have your CH3. This is your CH3. And then I do have my second carbon next to it. Now, as you practice more, as you're going to be faster. So this carbon here has 2 hydrogens around it. Do you see that? So this is going to be a CH2. They are connected to each other. And then you have another CH2 here. So that is a CH2. You have a fourth CH or third CH2 in there. Okay, different color. Here you go. So this is going to be a CH2. And then last but not least, you have your CH3 in here. So this is going to be your CH3. Now, as much as you can condense it, if you have parts of the molecule that are the same, you can simply group all of those together. So see what I have here? I have all of these CH2s that are the same between the 2 CH3s. So I can group all of those together and put them between parentheses and put the 3 in there. This means I know when I see something like this, I know that every carbon needs to be having 4 bonds in there. So there is no way but having all of these CH2s between the CH3s in there. Okay, so that is going to be the condensed structure. Now for the skeletal structure. Skeletal, I do not show hydrogens, I do not show carbons. I only need to show bonds. And to show bonds, normally we show them in a form of a dot. So every carbon is going to be represented by a dot. However, pay attention that carbons have a tetrahedral geometry, right? So let's say if we are working with a CH4, whenever you want to draw it, you want to make sure that you have a tetrahedral geometry and a bond angle between the bonds in line of a 109.5, because every single carbon is an sp3 hybridization. Okay, so that is an sp3 hybridization because all of those they have single bonds, so it's an sp3 hybridization for each one of those carbons in there. So it doesn't make sense that they exist as a straight line bonded to each other. So this is why when you represent any skeletal structure, you have to represent it in a zigzag way. What does that mean? This means one carbon needs to be down, the other carbon needs to be up like that. So I have 5 of them. I have a carbon here, I have a carbon, I have a carbon, I have a carbon, and I have a carbon. So 5 carbons in there. Just go ahead and draw 5 dots, but please draw them as a zigzag. Do not draw them as connected to each other by a straight line like this. This is wrong and it is not right. So we're going to draw them as a zigzag, and this is the 5 carbons, and then we're going to go ahead and connect them together. Okay, so by connecting them together, see how I read it. I start always reading from this side over here, and I have this is as a carbon. This is as a carbon. This carbon is connected to one bond, so definitely it needs to have 3 hydrogens on it. Normally, the carbons on the edges are CH3s. The carbons in between, if there is not any other branch coming off these carbons, then these are CH2s in there. Because this carbon is connected to 2 bonds, then definitely you're going to end up having 2 hydrogens in there. I can go ahead, this is the same as this guy over here, but you don't have to show it. You don't have to show the hydrogens, but I'm just showing you that every single carbon from those carbons in there, they should have an sp3 hybridization. So, and they should have 2 bonds in plane. And normally, as I said, to place the 2 bonds in plane, make sure that the long carbonate chain is one of the bonds in plane. That will make it so easy. So you have your hydrogen and the carbonate chain is in plane, 1 bond behind and the other one in front for every single carbon in there. And this is going to be the representation of the actually this is what this skeletal structure means, but please stick to this structure here. Don't show any hydrogens, but I'm just showing you what does that mean. Okay, so that's the skeleton form. Let's go ahead and do another example. Now in this example I've included a heteroatom, which is a chlorine in this case. So here you go. And let's open a page. Okay, and let's go ahead and work something similar to this problem. So we have a CH3, we have a CH, we have a chlorine, and we have a CH2, and then we have a CH3. Okay, something like that. And this is, as you can see, you see no bonds in there, so this is the condensed form. And I'm asking you over here, go ahead and draw the skeletal. So to draw the skeletal, the first thing that you do, again, we're going to start from the left and we're going to count the carbons. So I have 1 carbon, I have 2 in there. Anything which is in parentheses, I'm just going to ignore for now because I want to go ahead and draw the backbone. So it's going to be 1, 2, this is a 3, and this is 4. So I have 4 carbons in there. I'm going to go ahead and do 1, 2, 3, 4, and I'm going to go ahead and connect them together. Now, after you do this, now we go over 1 carbon at a time. So the first carbon here is my CH3. Okay, so I'm done with that. And then coming to the second one. The second one is the CH. Now, what do we have on the CH? This is the CH in here, and that CH has chlorine on it. See this parentheses there? This parentheses belong to the CH. So I know that the chlorine belongs to the CH. So all I need to do is do a branch and do a chlorine in there. Okay, and then I have next to the CH, I have a CH2. So this is going to be my CH2. And then I have my CH3 there. In both the skeletal form, and I'll draw the structural in a moment, and the structural form, I want you to show the lone pairs, please, because this is where our reaction normally starts. So always, if you have a heteroatom, whether it's an oxygen, carbon, nitrogen, sulfur, please, phosphorus, please show the lone pairs in there. So let's go ahead and draw the structural out of this one. And the structural here, we start with the carbon, with the CH3. We have our CH3 here. It's very simple as you read it. And then I have next to it a CH. So that is going to be a CH. The structural, you show everything. Now, see, I have this carbon having 2 bonds and the hydrogen. So it's a 3 bonds. So I definitely know that the Cl needs to belong to this carbon for the carbon to be octet. So I have my chlorine in there, and then I have a CH2, and then I have a CH3, and that will be the skeletal form of this structure. Okay, so let's have another example. Another example is this guy over here. You're given the condensed, and you're asked to draw the skeletal and the structural formula. You guys, again, whenever you have, at the beginning, whenever you have a parentheses, a compound with a parentheses, that compound needs to belong to the part of the molecule that is adjacent to it. So here I don't have any part of the molecule which is adjacent to the left, so it's definitely belonging to the CH in there. Okay, so I have 2 CH3s that that belong to the CH. We call those a branch. And then you have your CH. The chlorine now belongs where? It belongs to the CH. The chlorine cannot belong to the CH2, or else the carbon will have 5 bonds. So it needs to belong to the CH, and then you have a CH3 in there. So to draw the skeletal form, as I said, we're going to go ahead and count the carbons and ignore anything in parentheses. So we're going to go ahead and ignore the CH3s, and we're going to count the carbons. We're going to count this carbon, this carbon, this carbon, and that carbon in there. And we're going to go ahead and draw those. So it's going to be this carbon, this carbon, this carbon, and the other one. And this is the skeletal form, starting with the skeletal form here. So this is going to be the CH. So this carbon is going to be this one. And the CH has on it 2 CH3s coming off. So the 2 CH3s are going to be 2 dots. A CH3 here and a CH3 there. Guys, remember that a dot at the end of the chain is a CH3. So you have 2 CH3s coming off. This carbon, which is a CH, this will take you a time to get used to it, but you will. And then you have your CH, and then you have your CHCl in there. And then on the CH, you have what? You have a CH2 and a CH3, and this is the CH2, CH3. Please, again, show all lone pairs. Let's have another example. Again, as you can see, structural formulas can be complicated once you have branches in there. So in this case, it's easier for me to move one atom at a time. So I have my carbon in here. So this is going to be my CH3. So that is going to be my CH3 in there. Okay, or during the condensed. Now, next to the CH3, I have a CH or a C. So you have your C in there. Now, what do you have on the C? Look, what do you have on the C? You have a branch on the C. You have a CH3 coming off the C, and you have another CH3 coming off the C. Do you see that? So you have 2 CH3s coming off this carbon. So all I need to do is, because they belong to the carbon, this is called a branch coming off the carbon chain, in there. So I'm going to go ahead and open my parentheses and have these two CH3s coming off the carbon. Let's move on. You have a CH and the bromine coming off the CH. So you have your CH in there. This is the carbon. This is the carbon here. This is the CH. And you have a bromine coming off the CH. So go ahead and put the bromine in parentheses. Next to that, you have another CH. So you have another CH in here. But now what do you have on that CH? You have two groups coming off the CH. You have a CH2, CH3, and you have another CH2 and a CH3. Coming off what? Coming off this particular carbon in here. So I'm going to go ahead and open the parentheses and put those two groups because they are a branch of the CH. I'm just going to go ahead and put them on the CH in there. Okay. Now, every time you draw your condensed structure, look at it and see if you can condense it more. And here, yes, I can condense it more because see on this carbon, I start with a CH3 and then I have two CH3s coming off this carbon. So I can combine these two together and I can start from here and say this carbon has three CH3s on it. So I have my CH3 and then the rest of the molecule in there. That will be way easier to start with the condensed to convert that into a skeletal form. So once you want to convert it into a skeletal form, start with the last form of the condensed structure in there. And then, as I said before, we're going to go ahead and neglect everything in parentheses and count just the carbons that are connected to each other. So I have 3 carbons in there. Since I have 3 carbons in there, then I'm going to go ahead and put the 3 carbons as dots. And now I'm going to draw the branches that come off these carbons. On this carbon, I have 3 CH3s coming out. So these are the 3 CH3s. I have a bromine on the second one coming out, and then I have a CH2 CH3 coming out, and it's 2 of them. There are tons of examples in there. And there are problem sets that I posted again on eCampus with additional problems, so please work those out. Now, let's say, for example, if you include an oxygen in your formula there, everything stays the same. However, with the OH, you have to show the bond. You either have to show the bond or not. So it's really, it's up to you whenever you draw the skeleton form. So it's not a must to show the bond. And if you show the bond, it is not wrong, but only between the oxygen and the hydrogen. You cannot opt out the hydrogen here next to the oxygen. You cannot treat the hydrogen on the oxygen like the hydrogen on the carbon and opt it out in the skeletal. You have to show it for these structures in there. So we're going to start by drawing the structural formula. Start with the CH3 and then a CH2 and then a CH2. So I am reading as I am going here. So you have your CH3, you have your CH2. So here you go. This is the CH3, and then we have our CH2s, and then we have our a CH2 in there. And then we have our carbon that is connected. See, this carbon is connected. See how many groups are there around the carbon? 2 CH3s. I'm just going to go ahead and place them and an OH. Change this into skeletal form. Take away all the hydrogens except the one next to the OH. Keep it. Okay. Now, if your structure has a double bond, it's up to you for the condensed. You can either put the double bond or take it out. Because if you take it out, remember, every carbon has 4 bonds. So if I'm looking at this skeletal structure, I would easily know that between those 2 carbons here, so I have not these 2 carbons. It's actually, here you go. So between the 2 carbons, let's put the hydrogen back. And between those 2 carbons here, because it's a CH-CH. Now, this CH has a branch CH3 coming off, so it will satisfy the octet rule. But these two, if I keep a single bond between them, they will be 2 electrons short. Each one will have 6 electrons. So this is why I know that I have a double bond in between. You can either keep the double bond or take it out. No matter what you do, both structures will be right. So we're going to start with a CH3 and then a CH2 in there. So CH3, CH2 coming to the CH. So that is a CH. In between, there is a double bond. Put the double bond or take it out, and then you have a CH. On that CH, you have a CH3 as a branch, and then another CH, and as a branch on that CH, you have a CH2, CH3, and another CH3. So we're going to put both in brackets in there. Okay. Now for the triple bond, as I said, you have 2 options. If you are changing this into a skeleton, into a condensed form, let's change it into a condensed form. So if you want to change this into a condensed form, then it's going to be 2 CH3s that are connected to the CH, and then you have another CH in there. I can either keep the triple bond, okay, or I can take it out. So I can either represent it like this, which is more preferred, or I can take it out. So you have a CH, you have a CH, and then you have a carbon. Notice here, I have a carbon in there, so I immediately would know. And again, there is no bond here, so I'm just gonna take that bond out. So immediately I would know that definitely this carbon will have 3 bonds in there, so it will be a triple bond. Whenever you are representing a skeletal form, please make sure to stick to the bond angle. And the triple bond is linear. So every time we represent a triple bond, the carbons that are adjacent to it, so this carbon here and this carbon here, they are forced to be 180 degrees. Okay, so you cannot, and this is wrong. You cannot do this. You cannot do a triple bond and then do an angle and then do a branch here and then a branch there. This is wrong, so there is no angle in there. It's a simple straight line. It's a simple linear geometry. So condensed structures with a CO. Last time we talked about CO and said, like whenever you have a carbon next to an oxygen, that is a carbonyl. Carbons are sp2 hybridization if they have a double bond, if they are double bonded with the oxygen. And there, every time you have a double bond on the carbon, whether it's a carbon double bond carbon or a carbon double bond O, both elements that are existing between the double bonds, they have to be an sp2 hybridization. So these 2 carbons are sp2, this carbon and the oxygen is going to be an sp2 hybridization. The oxygen is going to be an sp2 because it does have 3 groups around it. So you have a sigma bond, and the 2 lone pairs, they should reside in the sp2 hybrid orbital, leaving, if I want to draw the valence bond representation here, leaving the second bond, I'm drawing the pi bond representation for this structure here. So I know that every double bond, so to see this pi bond here, is an overlap of 2 p orbitals, and every p orbital has 1 electron. Please refer to the valence bond representation video. So when these 2 p orbitals overlap with each other, then they are going to make a pi bond in this case. So this is the pi bond representation. And then the sigma bond representation, you have a sigma in here. We know that you have the sp2 hybrid here, you have the sp2 hybrid there, and you have 2 electrons here and 2 electrons there. This is why the hybridization of this oxygen is an sp2. It's an sp2 because this carbon is an sp2 hybridization, so the hybrid sp2 orbital of the carbon, the hybrid sp2 orbital of the oxygen, they overlap, they make a sigma bond. We will hit on this in chapter 3, but just a quick note that there are different functional groups that include carbonyls. And these functional groups, these are the reactive site of the molecule. This is where the reaction starts. So carbonyls exist in different forms in organic. Carbonyls can be connected to a hydrogen. We call this part an aldehyde. If it is connected to a carbon, then we call it a ketone. If it is connected to an OH, we call it a carboxylic acid. And if it is connected to an oxygen and a carbon, we call it an ester. And if we have two carbonyls separated by a carbon, we call it an anhydride. Give yourself some time in there because these we will hit on those in the chapter number 3. These are called functional groups in there. Okay, so let's say, for example, for now, we're gonna learn how to draw these molecules that include oxygens in there. So let's say we have this skeletal form, um, and let's go ahead and change that into a condensed form. So to do this, we're gonna start from this end over here, and I would always prefer to neglect, okay, all the branched carbons. So this means that I'm just going to go with the main chain, and the main chain is this one, the zigzag one. So this is going to be the main chain in here. So you have an oxygen. So all of this is going to be my main chain. Okay, so this is what I have. So we're going to start with um, a carbon. So you have your carbon in here. Let's go ahead and highlight that. Okay, so we're going to start with this carbon there. And this carbon is actually this carbon. Now, on this carbon, I have 3 CH3s. So you're going to go ahead and draw them. So move one atom at a time. And then next to this carbon, I have a CH2. Just go ahead and draw the CH2. And then I have my CH. Okay, now on that CH, I have what? So this is going to be my CH there. And on that CH, I have my ethyl group. So I have my ethyl group here, or my CH2CH3, since we didn't start with the naming. So I have my CH2CH3 in there. Notice how did I draw it? I drew it as a CH2CH3. I didn't draw it as a CH3CH2. That will be wrong because it's the CH2 that is connected to the CH. So pay attention to that. Okay? And then I have next to that, I have a CH2. Go ahead and draw it. And then I have a CH. Next on the CH, I have again a CH2, CH3. So go ahead and put it in parentheses. Move along, you have a CH2 and then an oxygen next to it. Do you see that? So you have a CH2 and an oxygen. Just put it as is. So the way that you say it, just go ahead and put it. And then you have a CH2 over here. So this is going to be my CH2. So what I've reached till now is, so I have my CH2 here. And this CH2 is this guy over here. Okay. Now, next to the CH2, I have a carbonyl. We agreed last time that we're going to represent carbonyls as COs. So this carbonyl here will be represented as a CO. So this is going to be a carbon and an oxygen. Next to it, there's a CH2, another CO. Okay. Now, next to the CO, you have an oxygen. So this is why, since I'm drawing a condensed in there, I'm just going to go ahead and combine both oxygens together and say C and two O's. Okay. Because it's better than saying a CO and another O. See, this is why we combine both and we make them a CO2. And then next to the oxygen, there is a CO. So we're going to go ahead and put the CO on the side. So this is going to be my CO, and that is going to be my CO. Don't neglect that. So you have the CO2CO. The CO2CO represents all this part here. And then next to it, you have a CH2 and then the CH. And then on that CH, you have a CH3 as a branch. And then see what do you have? You have a C and an O. And don't forget, this is a terminal aldehyde. So this carbon here, if I leave it as is, it's a 3 bonds. It's a bond and 2 bonds here. So definitely there is a hydrogen in there. We don't have to mention all hydrogens in the skeleton. We don't actually. So this is the true representation, but please remember that there is a hydrogen in here. Aldehydes, whenever we want to represent them at the end of the chain, these are CHO represented, not a COH. There's a difference between an alcohol, which is a COH. Let's have an example. There's a difference between something like this, which ends up with an OH, okay? And something like this, which end up with an aldehyde. There's a big difference in here. So if I want to go ahead and draw the condensed structure of the alcohol, this is called an alcohol. So if I want to draw the condensed structure of the alcohol, there's going to be a CH3, a CH2, and I have two of those, actually three, okay? And then I'm going to end up having my OH in there. Here I have my CH3, I have a CH2, and then I have a CHO. This is how I do it. I do it as a CHO. I don't do it as a COH because this is wrong and it will be confused with an alcohol group. And there's a big difference between an alcohol and an aldehyde. This is one type of functional group. Actually, these are two types of functional groups in there. An alcohol is one and an aldehyde is another. Cyclic structures, hydrocarbons can also be combined in cyclic structures in there. So the cyclic structure can either be a three-membered ring, four-membered ring, and five-membered ring. And we're going to stop at the six-membered rings. We're not going to do more than that. As you can see, if you want to combine three carbons in a cycle, the structure will be very branched, so it's easier to represent it in the skeletal form. And to do it in the skeletal form, simply draw a simple triangle in there. Draw all the three carbons and bond those together. This is how you represent the condensed and the skeletal. You do the same for the four-membered rings, the five, and the six-membered rings in there. For the six-membered rings, every carbon in here needs to be a CH2, right? So you condense it as a CH2, and we normally draw it as a cycle. To draw this cycle, all what you need to do is just to draw the six carbons in there. So these are three, and then you have the other three, and then connect all of those together. This is how you draw your cycle of six-membered rings in there. We will learn the nomenclature of each one of those as we proceed. Also, skeletal structures, they can have charges. However, when I show charges, I don't show lone pairs. So you have to remember that every time you have a positive charge, carbon needs to have three bonds to have a plus charge, and to have a negative charge, carbon needs to have three bonds and a lone pair to have a negative charge. So this over here is exactly the same as this structure. This is the skeletal structure for both, and this is exactly the same as the structure. In any type of representation of these structures, I always take out a hydrogen from the octet in order to place the charges, whether it's a positive or a negative in there. Okay, there are more additional practice problems. Let's go ahead and try to solve a couple of those. So let's do D, for example. We're going to go ahead and draw the skeletal form. So as we said, for the skeletal form, we're just going to go ahead and ignore every single carbon that belongs to the parentheses. And now I'm going to go ahead and draw these four carbons in here. Okay, and then I'm going to connect them together. So starting with a CH, so that is going to be the CH. The CH is connected to what? It's connected to two groups of CH2OH. I'm starting with the CH2, guys. So that is going to be my CH2, and that is going to be my OH. Put the lone pairs. And I have another CH2 and OH in here. And then I have my CH2, which is 3 in there. So yeah, I've missed this. So I thought that this was a branch. When it's a CH2, guys, do not miss it. But when it's a CH in parentheses, yes, you can go ahead and opt that out. But if it's a CH2, please don't miss it. So let's go ahead and take those two out. And we're going to add our CH2s in there. So we have 3 of these CH2. So you have your CH and you have a CH2, another CH2, and then a CH2 over here. These are the 3 CH2s. And then you have a carbon in here. On this carbon, you have two CH3s. This is a CH3 and another CH3. And then you have the CH2, and then you have a CH3. Okay? So again, whenever you have CH2 between parentheses, don't opt that out because this is considered to be condensed more and it's part of the chain. So now your total number of carbons in the chain is 1. 3 of the CH2s, this is 4 carbons, 5 carbons, 6, and 7. So this is going to be, let's go ahead and highlight it. It's going to be 1, 2, 3, 4, 5, 6, and 7. And then you go ahead and you put your branches on that. For B, I'm starting with this carbon over here. See, it's now a CH3 in parentheses, so I can opt that out. But if it's a CH2, don't opt it out. So for A, if it's a CH2, don't opt it out. Consider it part of the chain. So we have our carbon here, and then we have another CH. This is it. And then we have, so that is the CH. And then we have a CH2, which is going to be here. And then we have a CH3, which is going to be there. And then we're going to go ahead and add all of those together. Starting with the carbon, it has a 3 CH3s on it. So these are the 3 CH3s that are connected to the carbon. Next to that, you have a CH. Now that CH has what? It has an OH on it. So this is going to be the OH. And then you have a CH2, and then you have a CH3, and pretty much that's it. For C, this is an aldehyde. See, this is a CHO, so this is going to be an aldehyde. So I'm going to start with my CH. I'm going to opt out the CH3s for now. I'm going to start with the CH and connect them to the carbon. So I have 2 carbons in here. Okay, so I have a carbon and I have another carbon. Let's go ahead and connect those 2 together. Now, this carbon, the CH, has how many carbons on it? It has 2 CH3s on it. So this is a CH3 and this is a CH3. And then I have my C, this is a CH, and then I have my CHO. So this carbon in here is going to be my aldehyde. So I need to put the aldehyde in there. So I have to put the aldehyde, and it's up to you. You can show the hydrogen, or you can opt it out. So if you want to opt it out, it's fine, and it's going to simply look like that. Okay, these 2 are exactly the same. Okay, so this is, I believe, the end of this part.